oil control valve sticking. This directly impacts emissions and drivability because the intake and exhaust valves aren't operating at their optimal points in the combustion cycle.
The cooling system is also essential for overall engine health. What are the key checks a technician needs to perform there?
The cooling system needs to be inspected as a whole. Pressure testing identifies internal or external leaks and checks the radiator cap's condition. You verify engine operating temperature using a gauge or pyrometer, and always check coolant level and condition for contaminants. It's about ensuring efficient heat transfer.
And for fans and fan clutches, which are designed to keep that temperature regulated, how do you diagnose problems with them?
For mechanical fans, look for a wobble or bent blades. Fan clutches are often diagnosed by looking for fluid loss, indicated by oily streaks, or by checking their resistance when turned by hand. They should offer some resistance when cold and more when hot. Electric fans are controlled by engine coolant temperature switches, or AC switches, so diagnosing them requires consulting wiring schematics.
That brings us to electrical diagnostics, where schematics are absolutely vital. What makes them so critical for technicians?
Electrical schematics are the roadmaps for any electrical circuit. By understanding the symbols, a technician can identify the power source, whether a device is voltage or ground controlled, and what other components share that power. They reveal pin numbers, wire colors, fuse locations, splices, and ground points. In essence, they allow a technician to efficiently trace and understand current flow and pinpoint electrical issues.
Moving to the battery and charging system, its role goes beyond just starting the engine. It's crucial for stabilizing voltage. What are the key diagnostic tests for battery-related issues, including excessive drain?
Low battery voltage or poor connections cause slow cranking. The charging system maintains stable voltage during operation, but fluctuations can reset computer sensor inputs, causing drivability problems. Parasitic load is the current draw from computers when the vehicle is off. To measure this, you connect a digital multimeter in series between the negative battery cable and post, ensuring all accessories are off. Most manufacturers allow 50 to 100 milliamps. Anything higher needs further diagnosis.
And specifically for the starter, how do you perform a current draw test, and what does it tell you?
A starter current draw test requires a battery with a specific gravity of 1.190 or greater. With all electrical loads off and the ignition disabled, you crank the engine while observing ammeter and voltmeter readings. High current draw with low cranking speed usually indicates a defective starter or internal engine problems. Conversely, low cranking speed with low current draw but high voltage points to excessive resistance in the starter circuit, often in the cables or connections.
To pinpoint that resistance, voltage drop tests are essential for both starter and charging circuits. How are those performed?
For the positive battery cable, connect the voltmeter across the cable from the battery post to the starter solenoid terminal and crank the engine. It shouldn't exceed 0.5 volts. For the solenoid itself, test across its large terminals. It shouldn't exceed 0.3 volts. And for the negative battery cable, test from the starter motor housing to the negative battery post, aiming for less than 0.2 volts. Any higher reading indicates excessive resistance in that section of the circuit.
So, charging system failures can lead to engine performance issues beyond just a dead battery. What are some of those impacts?
The charging system's primary role is stable electrical system voltage. Undercharging or overcharging can cause hard starting or battery gassing. A defective diode in the alternator, for instance, can allow AC voltage leakage into the electrical system, which disrupts normal computer operation. If output is zero, it could be an open field circuit. If it's normal, but no current reaches the battery, check the fuse link. Low output despite good belt tension means the alternator itself is defective.
Now, let's delve into the ignition system. What kind of problems stem from ignition issues, and how do we even begin diagnosing them?
Ignition problems manifest as no starts, hard starts, misfires, poor drivability, spark knock, power loss, or poor mileage. Modern systems are either distributor ignition, electronic distributorless ignition using waste spark, or coil on plug systems, all often computer controlled. The first step is always checking for spark. If no spark, you isolate whether it's a primary or secondary circuit issue. Testing the primary circuit with a test light or scope shows if the coil is switching. If it is, the problem is in the secondary windings or components like the cap, rotor, or wires. An oscilloscope can offer detailed pinpoint testing. And a wet test, spraying water on secondary wiring, can reveal voltage leaks. Also, technicians must consider the root cause. For example, a shorted coil winding can prematurely destroy a new ignition module.
And DTCs, or diagnostic trouble codes, often point us to a general area. How do they help with ignition diagnosis specifically?
DTCs, retrieved from the PCM, indicate a problem area, not necessarily the exact cause. You then consult the service manual for pinpoint tests. Some systems are more sophisticated, setting codes for primary ignition components like modules, while others might only flag spark timing control issues. Always use the manual to guide the detailed diagnosis after retrieving a code.
What about the physical components of the primary ignition circuit? What are common failure points there?
Primary circuit faults are often bad connections at terminals and connectors. Probing wires to test insulation can damage it, leading to corrosion and high resistance. Technicians should test for unwanted resistance and current carry capacity using voltage drop tests or an ohm meter. When replacing wiring, the correct gauge must be used and connections should be soldered and sealed. Components like the ignition switch or ballast resistor are tested with a DMM, always checking both power and ground circuits.
And the secondary ignition circuit handles very high voltages. What should technicians be looking for there?
Visual inspection is key. Look for chafing against metal, proper routing to prevent crossfire, and coolant or oil-soaked wires or boots. Check spark plug wire terminals for corrosion or arcing damage. Wire resistance can be checked with an ohm meter. Distributor caps and rotors should be inspected for burns, cracks, or arcing damage. An ignition oscilloscope can confirm secondary voltage leakage, especially during a wet test simulating damp conditions.
Ignition coils themselves are critical. What specific checks are involved for them?
Inspect the coil for cracks or leakage in the tower and for oil leaks from the container, which indicates internal condensation and potential voltage leaks. With an ohm meter, primary windings typically measure 0.5 to 2 ohms, and secondary windings 8,000 to 20,000 ohms. An engine analyzer can test maximum coil output, always referencing manufacturer specifications.
Triggering devices are vital for correct ignition timing. What types are common and how are they tested?
Common types include magnetic pulse generators, Hall effect switches, and optical pickups. Magnetic pickups can be tested with an ohm meter for resistance, shorts, or opens, and also for AC voltage output with a DMM or waveform with a scope. Hall effect and optical pickups require a voltage feed and ground, and their signal line is best tested with a lap scope, ensuring the square wave signal reaches 90% of reference voltage when high and within 10% of ground potential when low.
Moving to the modules themselves, like the ignition control module or powertrain control module, how do you test these complex components and what precautions are needed during replacement?
Specialized testers check the module's ability to switch the primary ignition circuit. If the module tests good, then circuit tests are necessary to confirm wiring and signals. For replacement, always follow manufacturer procedures. Dielectric silicone grease is often required for heat dissipation on ICMs. For PCMs, always test power and ground circuits and outputs first, and always ground yourself with a strap to prevent static discharge from damaging sensitive circuit boards.
Let's turn to fuel, air induction, and exhaust systems. Fuel system issues can be incredibly varied. What's the diagnostic process for them?
First, identify the system type and review its operation. Then verify the customer's complaint. Check for any relevant TSBs. After that, perform pinpoint tests of the fuel delivery system to find the exact cause. It's crucial to identify the root cause, not just replace a failed part. For example, a fuel pump failing due to tank debris means replacing the pump won't fix the underlying contamination. Lack of fuel causes power loss, hesitation, or surging. Excessive fuel from high pressure or leaking injectors causes flooding, misfires, or poor economy. Restrictions in air or exhaust also reduce power.
Fuel system DTCs can sometimes be misleading.
How do you interpret them correctly to avoid misdiagnosis?
Fuel system DTCs usually identify a system problem, not a specific component, because the computer can no longer properly control the air-fuel